This short video discusses the basic principles and construction of a static Fourier transform spectrometer. In these types of devices, dispersive elements are used, but in an interferometer configuration. In these devices, a fringe pattern is formed in space, which is then Fourier transformed to extract the spectral information. A good example of this is the spatial heterodyne spectrometer demonstrated by Harlander in 1991 and shown here. Here, light from the target source enters the spectral device, is then split via means of a beam splitter, and passed onto two reflective diffraction gradients shown here. The light then passes back through the beam splitter, interferes, forming the fringe pattern, which is then imaged onto the detector, and the information can then be extracted. The advantages of these devices is they have no moving parts, but has the same attenuate or throughput as a classic Fourier transform spectrometer. The system has superior light gathering potential, for example, when compared to a Chesney-Turner device. This makes the system ideal for gathering light from large attenuate targets. What do we mean by this? Well, here I have four examples of how one might make a transmission Raman measurements. So laser light hits the target sample here and is then dispersed through the sample and measurements made from the coloured area in each case. In the first case, a small area is imaged from a modest field of view and light passed through into a classic Chesney-Turner or dispersive system, and no light is lost. However, if you wish to gather light from a larger area, as shown here, then you must use a larger attenuate spectrometer, such as the HES range of spectrometers offered by IS instruments, which use this static Fourier transform configuration. An alternative is to dramatically reduce the field of view and then image from the same area. This loses a lot of light but allows you to use a classic dispersive system, as shown here. Or you may wish to gather light from a larger field of view. In principle, the HES range or static Fourier transform spectrometer could also be used to make a measurement in this setup. So what are the key considerations when thinking about using a static Fourier transform device? Well, first, the resolution is a function of the number of lines imaged, not the slit width. System throughput can be several orders of magnitude greater than in a dispersive system, and the systems require no slit. In fact, ISI have demonstrated systems with full operation compatible with 3mm fibre inputs, giving them up to 500 or even 1,000 times greater throughput than a classic Chesney-Turner device, for example. However, the initial information is acquired in image space, not spectral space. This means the noise is also presented in the image space, leading to the so-called multiplex disadvantage. Therefore, in order to realise the full potential of these devices, one must make measurements from targets when the attenuate is large, otherwise the full benefits will not be achieved. For further information, please contact IS Instruments. The contact details are shown here. Thank you for your time.